our topic for the day is capacitors and capacitance. So before we start talking about the concept of capacitors and capacitance, I want to very briefly review the relationships for inductors that you guys should have gotten in the lecture video on Friday. Okay. So for an inductor, L, that has some voltage across it, let's call it VL of T, and some current flowing through it, let's call this IL of T. You should have at least seen the following relationships. So the voltage drop across an inductor, VL, is equal to the inductance times the derivative of the current with respect to time. And two important things that we can glean from this particular relationship is that an inductor looks like a short circuit in a DC system. And the second thing is that the current through an inductor cannot change abruptly. The second relationship is simply the first relationship rearranged. So the current flowing through an inductor can be expressed as 1 over L times the integral from negative infinity to some point in time t of the voltage drop across the inductor as a function of t prime, where t prime is just a dummy variable representing time, because I can't have t in the limits of my integration and it also be inside my integral. And this can be expressed as the integral from some time t naught to t of VL of t prime dt prime plus IL at t naught. So we can see from this second representation here that the current flowing through an inductor depends on past values of the current flowing through an inductor. So in some sense, an inductor actually has a little bit of memory. That's how it works as an energy storage element. All right. The third relationship was for the power absorbed by an inductor. It will always be the product of the voltage flowing through and, voltage across and current flowing through the element. And it can be expressed purely in terms of the inductor current as L times IL times DIL by dt. And then lastly, the energy stored by an inductor is 1/2 L times IL squared. So those are our four relationships. We could use relationships 1 and 2 to figure out that inductors in series combine like resistors in series, and inductors in parallel combine like resistors in parallel. All right, so the reason why I took the time to show you all of these relationships is because we are going to get almost exactly the same relationships for capacitors today, except that everywhere we see voltage, we'll replace it with current. Everywhere we saw current, we'll replace it with voltage. And then everywhere we see L, we'll wind up replacing it with C. They are literally the exact same constituent relationships, except that we swap the role of voltage and current for capacitors and inductors. So they are what are known as electrical duals of each other. In an inductor, energy is stored in the magnetic field. In a capacitor, energy, we'll find out, is stored in the electric field. Everything about them is just swapped around. Okay. So with that being said, let's first look at the physical characteristics of a capacitor. Okay. So the most common capacitor that's seen is the parallel plate capacitor. And the parallel plate capacitor, as the name suggests, consists of two parallel plates, like so. And I'm going to call this plate, unsurprisingly, the top plate. And this plate down here, unsurprisingly, the bottom plate. The area of the plates is important, so I'm going to characterize this dimension as the length of the plate. This dimension as the width of the plate, so that the area is simply L times W. And separating the two plates, we typically have what's called a dielectric material. Bless you. The dielectric material provides physical separation between the two plates and has a giving us a distance d that separates the two plates. So this is what a physical capacitor might look like. The plates don't necessarily have to be rectangular by any stretch of the imagination. In fact, the overwhelming majority of parallel plate capacitors have circular plates. You might also see parallel plate capacitors in the form of cylindrical capacitors, where effectively you take your two plates separated by a dielectric medium and literally roll them up into a cylinder and then put it in a housing, which is a very common form factor that you see in most modern electronics. So if you ever crack open your computer case or anything like that, all those big cylinder things are capacitors. The distance between the plates. Could be thought of also as the thickness of the dielectric material. So let's talk a little bit about how capacitors work, because this isn't super obvious, okay? This is a circuit element, and so we expect to see some relationship between the voltage and the current, okay? Now, the most obvious question that you guys may be asking is, how can there be a current flowing in this device at all? There is something physically separating the top plate from the bottom plate, which means charge shouldn't be able to travel through because there's not a conducting medium there. Most dielectric materials are very, very good insulators for this specific purpose, okay? So what do you guys know about the physics of electrons and protons and all that kind of good stuff? You're working on it, okay? So at a basic level, if I have let's say, an electron, and I try to move another electron near it, what's going to happen? They oppose each other, right? There's a repelling force, okay? So if I were to apply a voltage, positive polarity on top, negative polarity on bottom, like so, what would wind up happening is that the electrons, I'm going to draw it as a little dot, like so, that make up whatever conductive material the top plate is made of, would be attracted towards the positive polarity terminal of our voltage source, thereby leaving behind some positive charge Q plus, right? And every electron that moves off makes it harder and harder and harder to sustain that positive charge on the top plate because they're all repelling each other. Or we could think of it in another way, as if the positive polarity terminal of our voltage source were putting positive charge protons, I guess you'd call them, onto the top plate, and every single one of them on there makes it harder for the next one to get put on, right? We would also see the exact same amount of charge, but of opposite sign, accumulate on the bottom plate, because this has to be a balanced system, because the law of conservation of charge, right? So if we're accumulating positive charge on the top plate, we have to be accumulating negative charge on the bottom plate, so such that the total charge on the capacitor has to equal to 0. Charge has to be conserved. So in this situation, we are forcing charge movement effectively. And whenever we have charge moving, we should observe a current, right? If we were to take our voltage off, what would happen? The charge would release, meaning the charge would be moving off of the plates, and we would also have charge movement. So while we don't have a current in a traditional sense flowing through the device, it looks like that's happening. What it's really called is a displacement current, because we are displacing charge carriers on and off the plate, and their movement on and off the plate looks like a current. Okay. So let's talk about the relationships that govern these things. Okay. So charge Q is equal to the capacitance C multiplied by voltage V. So our capacitance C is then the ratio of charge to voltage, meaning that its units are coulombs per volt. A coulomb is an amp second per volt, and we call this a farad F. So these are the units of capacitance. As I said earlier, capacitors wind up storing energy because of the sustained electric field within them, right? So for an inductor, we have a coil, or we have a wire carrying a current that generates some magnetic field. We coil up that wire, causing a concentration of magnetic field or a high concentration of magnetic flux, and that is our energy storage mechanism for an inductor. Well, in a capacitor, if we have positive charge stored on one plate and negative charge stored on the other plate, we wind up getting, let me do it in blue, electric field lines oriented from the positive charge down to the negative charge. And sustaining this electric field is the energy storage mechanism for our capacitor. As soon as we no longer have that voltage drop across it, so if we were to allow it to discharge, the electrical energy, the energy stored in the capacitor would slowly dissipate because the field would slowly get smaller and smaller and smaller until all of the charge moved off the plate. Okay. So what affects the capacitance of a system, right? Well, capacitance is dependent on the geometry of the system as well as the material properties of the dielectric by the following relationship. So we're going to have epsilon WL divided by D, right? So WL and D are geometric properties of the system, okay? So the more area that our capacitor plate has, the larger its capacitance value will be. Similarly, the smaller the separation between the plates, the larger the capacitance value will be. For most capacitors that are built in a manufacturing facility, this distance between plates is on the order of microns, so micrometers or smaller. A very, very, very thin gap between the plates. The cross-sectional area of the plate is usually on the order of a few square millimeters. Okay. So we get millihenries to microhenries worth of capacitance out of a system like that. If we wanted to get a 1 farad capacitor using conventional fabrication techniques, it would probably be the size of that cabinet. Like large capacitor values on the order of 1 farad are in extremely rare cases. Think rail guns and things like that, like where you need a ton of energy storage that you need to be able to dissipate very, very quickly is really the only reason you would ever have a large capacitor. Okay. The other contribution here is this term epsilon. And this term epsilon is actually the product of two things. Okay. So epsilon is really epsilon R times epsilon naught, where epsilon R is the relative permittivity measured with respect to epsilon naught, which is the permittivity of free space, or the permittivity of a vacuum. The permittivity of free space has a value of 8.854 times 10 to the negative 12 farads per meter. And then everything else is measured relative to that. So for instance, the relative permittivity of silicon, I believe, memory serves me correctly, is 11.9. And then you would multiply that by the permittivity of free space. The relative permittivity of deionized water is 81. The relative permittivity of mineral oil and things like that that are used in a lot of transformers and electrical systems, depending on what the oil is, can be anywhere from 4 to 20, just depending on what kind of additives and stuff like that we put in there. The permittivity of air is only very, very slightly higher than vacuum. So the relative permittivity value there would be like 1.001 or something like that. So air and a vacuum are roughly the same permittivity. So just trying to explain to you guys what types of things impact the capacitance values that we're going to see. All right. So let's now introduce the schematic representation of a capacitor. And we're going to have two of them. Okay. So the first representation for a capacitor that we might see is this guy right here, where it is two leads, and then we have two parallel plates. There's a gap in between to signify that there's not any actual current flowing through it. So much like the schematic representation of an inductor is simply a coil, the schematic representation of a capacitor is two parallel plates because that's usually what it's made of. It does. Very, very good point. So Christina here says that this schematic symbol looks close to that of a single cell battery, which if you go way back to our notes on the second day of class, a battery, I'm going to erase this in a moment, has a schematic symbol of this, which is why I pretty much never use the schematic symbol for a battery. I just use the generic DC voltage source because there is no confusion as to whether or not it's a capacitor. Okay. So for our capacitor, there can be some voltage drop across it, VC of t, and some current flowing through it, IC of t. And this is our symbol for a generic capacitor. And then over here to the right, I'm going to draw the symbol for what's called an electrolytic or polarized capacitor. Let me make that curve more prominent. So here's our value of C. Here's VC. Here's IC. And so this would be electrolytic, also known as polarized capacitor. Okay. So you may see these two symbols used interchangeably. That's technically not correct. Okay. An electrolytic capacitor has a very specific positive polarity terminal and a very specific negative polarity terminal. And if you do not connect things correctly, it will literally burst. Okay. So how many of you have ever had a piece of electronics stop working? You open it up because you smell something funny, and you see that one of those cylindrical looking things, the top of it is kind of domed over. Nobody takes enough of their stuff apart anymore, apparently. So I wish I would have brought one of these. Effectively, if you were to buy an electrolytic capacitor, usually it looks like a big cylinder like this. It will typically have a stripe letting you know which one of these, and it may actually have positive signs on it, letting you know which one of these is a positive polarity terminal. The very top is usually a thin metal plate that's scored, so that if you ever disconnect or if you ever connect this electrolytic capacitor incorrectly, it's very easy to dissipate that extra energy. That's what's going on is a chemical reaction is effectively burning up all the electrolyte solution in there, and that scored top plate is able to deflect, which lets you know that this capacitor has failed, while still keeping all of the residual electrolyte inside of it so that it doesn't corrode anything else. So anyway, so like I said, you might see this electrolytic capacitor symbol used in other people's videos, possibly even in your homeworks and stuff like that. Every capacitor that we are going to be physically dealing with in this class is a non-electrolytic or general capacitor because I don't want to spend a whole bunch of money while you guys plug stuff in backwards and blow them all up. So it's more cost effective to just use the generic capacitors. Electrolytic capacitors are used a whole heck of a lot in power electronics, where you should not expect to ever see a negative polarity voltage across your capacitor. So anyway, so there's a built-in indicator that something's screwed up. All right. So now let's talk about our relationships. So our first relationship for capacitors is as follows. Capacitor current, by definition, will be the change in capacitor charge with respect to time. That is our definition of current from the second day of class. Now we know that charge is related to capacitance by voltage. So we could express this as C dV by dt, where we're making an implicit assumption here that the capacitance value of the capacitor cannot change. Okay. Realistically, we should also have a term plus V times the derivative of capacitance with respect to time, but if the capacitance can't change with respect to time, that term goes to zero, which is why we're not including it. And for those of you that want to suffer through me talking about those types of capacitances, come take my MSE 402 class next quarter, where we talk about all kinds of nifty things like MEMS devices, which measure signals by having changing capacitances. All right, so this is our first relationship. Compare it to the first relationship that we had for an inductor. Right. So it's literally the exact same relationship, except that we replaced L with C and we swapped the role of I and V. Okay. Exact same thing. So typically speaking, we would be in control of the voltage. So if we applied a time varying voltage, we should see some current. That being said, that brings us to our first consequence of this rule. What if we had a DC system where the voltage wasn't changing? What would our current be? Zero. Absolutely right. So in a DC system, capacitors behave like open circuits. And that rate of change relationship explains exactly why. If the voltage isn't changing, the current flowing through the capacitor must be zero. The element, so to speak, that we have that forces the current to be zero is an open circuited set of terminals. So anytime we see a capacitor in a DC circuit, we can simply take the capacitor out, call it a day. Now, in an inductor, we saw, or those of you that watched Friday's video saw, that the current flowing through an inductor could not change abruptly, because that would give us an infinitely large voltage drop, which would imply then that we would have an infinite transfer of energy in an infinitesimal amount of time. Okay. What do you think that particular relationship is going to look like for a capacitor? Right, the voltage can't change abruptly, because if the voltage changed abruptly, we would have an infinite amount of current, which would mean that we would be creating charge from nothing, which would be a violation of the law of conservation of charge. Okay. So the voltage drop across a capacitor cannot change abruptly. So you just asked, and I want to make sure I'm paraphrasing your question correctly. What would happen if we had a capacitance connected to a voltage source and we turned off the voltage source, right? Because that would look like a change in the voltage drop that happens very abruptly. Okay, so two things. A, it still takes time to turn off the voltage source. And B, what we will observe, this is actually getting ahead of the game here a little bit, because this is literally what we're going to be talking about in our next class meeting. But if we had a simple circuit like this. So I have a DC voltage source. Here's some resistance. Here's some capacitance. And here's a short circuit. No, that's drawn poorly because I need the voltage. Let me think about how the switch needs to work really quickly here. So I want it to have been connected. Bless you. You guys don't know about unit step functions yet, do you? Some of, not all of you. Yeah, I'm just trying to think of how to make this switch work the way that I want it. Effectively, it's where the switch is closed and then the circuit completes with just this path after the switch was closed. Oh, there we go. This is where my rotation needs to be occurring. So for a circuit like this, if we were to plot the capacitor voltage as a function of time, and this is to help answer Christina's question, right? Prior to our switch changing states, we would see that the voltage drop across our capacitor is constant. And it'll have actually a constant value of Vs for this thing. After our switch opens up, what we are going to find out after a fairly lengthy derivation on Wednesday is that our capacitor voltage will exponentially decay toward zero, and that the rate at which that exponential decay occurs depends on the capacitance value and the resistance value of the system. So from an ideal circuit element standpoint, it seems like If I just connected a voltage source across a capacitor and then I removed the voltage source, I would have a problem. However, we have to take into account that the wires and stuff like that are going to have some amount of resistance as well, so that every circuit we could possibly have will have some inherent resistance in it as well. That'll kind of smooth things out a little bit from a conceptual standpoint. Yes. So you're shorting a capacitor to de-energize it. It still takes time to de-energize it because that short isn't, there's no way to put a wire that contains zero resistance. So effectively what you're doing to short a capacitor to de-energize it, which is something that's done in a whole lot of troubleshooting of particularly power electronics, because you do not want to leave those capacitors energized. They literally have enough energy to kill you in them. You use special, it's like a screwdriver with a ground wire effectively. And you need to make sure that you have a thick enough wire so that you don't melt the wire, because it's what's going to absorb all of the energy transfer. Right, so it could be on the order of microseconds or nanoseconds, but it is not instantaneous. Yes. All right. So back to our mathematical relationships. Again, we will talk about this situation that we have here on the board in great detail on Wednesday's class meeting. So for our second mathematical relationship, we are simply going to rearrange our first relationship. And in doing so, what we will find is that the voltage drop across a capacitor is equal to 1 over C times the integral from -infinity to t, IC of t prime dt prime, which is the same as 1 over C times the integral from t naught, some point in time at which the capacitor voltage is known, to t of IC t prime dt prime plus VC at t naught. Once again, this looks almost exactly identical to our inductor relationship, except that we have swapped our L for C and swapped the position of voltage and current. For our third relationship, we'll talk about the power absorbed by a capacitor. So that's going to be the current flowing through a capacitor times the voltage drop across the capacitor. And substituting in mathematical relationship number 1, this looks like C times the voltage times the derivative of the voltage with respect to time. Finally, our energy relationship. If we wanted to derive this, it would be pretty much the exact same derivation that we saw with respect to inductors on Friday. So instead, I'll just move ahead to say that we'll have 1/2 C times the square of the capacitor voltage. So those are our 4 relationships for capacitors. Again, they are practically identical to those we saw for inductors, except that we just switch the role of current and voltage. So, as we're wrapping things up here, how do you think capacitors are going to combine compared to, and yes, Brody. Shit, no, Carson. Exactly right. So I like to put everything in terms of resistance because that's what you guys have the most experience with. But since resistors combine exactly like inductors do, your statement was very much correct. So we could derive this if you guys wanted to see me do calculus. But generally speaking, capacitors in series combine like resistors in parallel, and capacitors in parallel combine like resistors in series. All right, so I'm going to take a cue from Walker here, and I am going to pull up you guys' in-class assignment. We're going to talk through some of the things here. So this way I'm working examples while also we're getting some ICA work done. So if I'm not mistaken, this should be in-class assignment number 12. Okay. And actually, now that I'm looking at this, there's technically a typo here. This should be W max, not P max, because I'm asking you for energy, not power. So I apologize for that. At some point, I will actually remember to update that typo or actually come up with a new in-class assignment instead of just leaving that typo there for, I think, 3 years at this point. So, it is what it is. So let's talk about that. Okay, so let's look at part A here. Our goal for part A is to determine the maximum energy stored. And we know that C is equal to 0.2 millifarads. Additionally, we know that our voltage drop across our capacitor is equal to 5 plus 3 cosine squared 200t volts. So there are a couple of different ways that we could wrap our heads around this thing. What I am going to do is use a trig identity. Okay. So the trig identity that I personally am going to use is cosine of some angle 1 times cosine some angle 2 is 1/2 cosine angle 1 minus angle 2 plus 1/2 cosine angle 1 plus angle 2. Where in this case, angle 1 is 200t and angle 2 is also 200t. So using this trig identity, I would get 5 plus 3/2. So what's cosine of 0? Okay, so 3/2 times 1 plus 3/2 of cosine 400t. Now, what I'm going to do here is I'm actually going to plot this voltage waveform, because instead of going through the motions here, so let me scroll up here, right? So we are asked to determine the maximum amount of energy, and you guys to this point have been conditioned to say that whenever you want the maximum value of a function, you should take the derivative of that function, set it equal to 0 to find the time at which the maximum occurs, plug that value of time into the equation, and then go from there. And that's not wrong here by any stretch of the imagination. But we can think our way through things critically and get to a result that involves a whole heck of a lot less calculus, okay? And that's the one that I prefer, because I'm not super great at integrals and stuff like that. So if I were to plot this function of VC, what would it look like? So I would argue that I'm going to have some VC offset that is 5 plus 3/2 added together. So that would be 6.5, right? And then on top of that DC offset, I'm going to have a sinusoidal signal that is superimposed. Because we're dealing with a cosine signal, it should have its maximum value at t is equal to 0, and then it'll oscillate from there. So up here, this should be 8 volts. Down here, this should be 5 volts. And it should be doing roughly this number, right? Oscillating between 8 and 5 at an angular frequency of 400 radians per second. So I have 5 plus 3/2 is 6.5. And then I have this 3/2 here is the amplitude of my cosine function. So its maximum value is going to be at 1, and its minimum value is cosine is -1. So that's why it's adding or subtracting 1.5 from that 6.5 volt DC offset. So our goal is to find W max, where W as a function of time is 1/2 C times our voltage squared. So it should stand to reason here that we should expect to see the maximum amount of energy storage whenever our voltage is at either a minimum or a maximum, okay? Now, which of these cases is it going to be? Well, fairly obviously, when our voltage is at a minimum, we're going to have 5 volts, and 5 volts is significantly less than 8 volts, right? So we're only going to have maximum energy storage at these points, right? If we had had a pure sinusoid without any sort of DC offset, we might see maximum energy storage on the negative half cycle as well. But that DC offset pushes it to where Vmax is 8 volts. So we're going to have 1/2 times 0.2 times 10 to the minus 3. Let's see, a farad is a amp second per volt. Times 8 volts quantity squared. Throwing that in a calculator. Calculator. I'm going to have 0.5 times 0.2 times 10 to the minus 3 times 64. Looks like 6.4 times 10 to the minus 3. Let's look at our units here, right? So this volt here cancels out one of these here, so that in my numerator I have volts times amps times seconds. What's a volt times an amp? Watts, and a watt times a second is a joule. So 6.4 times 10 to the 3 joules, or 6.4 millijoules, which is exactly what we would expect. You could get this result by taking the derivative of that function, setting it equal to 0, finding a value for t that causes that function to be at its maximum and all that kind of stuff. But that level of calculus will take you 20 minutes for this ugly function because you'd have to do weird integration by parts and all that kind of good stuff. Whereas sitting down and kind of thinking about what you're given gets you there in, I would argue, a little quicker way. For part B, we need to determine the voltage present across the capacitor terminals if VC is 0 for t less than 0 minus, and IC is 8e to the negative 100 t milliamps for t greater than or equal to 0 plus. So let's write some stuff down here. We're trying to find VC of t. So if we're trying to find our capacitor voltage, let's look at the information that we know. VC of 0 minus was 0 volts. IC of t was 8e to the negative 100 t milliamps. So my first question is, which of our 4 relationships should we use? The second one, absolutely right. So we're trying to find voltage, so we should use the one that says voltage is equal to stuff. Okay. So VC of t is equal to 1 over c times the integral from t naught to t of IC t prime dt prime plus VC at t naught. All right, so let's start substituting things in here. So what was C again? All right, so I'm going to put 0.2 times 10 to the minus 3 amp seconds, and then I'm going to put 1 volt on top so that all my units are taken care of there. Here's my integral. At what point in time is my voltage a known quantity? Okay. We're going to integrate out to t. My capacitor current is a fixed value. So I'm going to express this as 8 times 10 to the minus 3 amps. So that's my 8 milliamps, e to the negative 100 t prime dt prime. And now outside of this integration, I need to add my initial condition, which was 0 volts. So I'm going to move my 8 milliamps to the outside. So I'm going to have 8 times 10 to the minus 3 volts times amps over 0.2 times 10 to the minus 3 amps times seconds. Let's cross some stuff out here. So this 10 to the minus 3 cancels this 10 to the minus 3. This amp cancels this amp. So we're left with 8 divided by 0.2. So that should be 40. How do I do that integral? So now I'm integrating e to the negative 100 t. How do I integrate that? Okay, so 1 over negative 100. What are the units on that negative 100, Patrick? Okay, so the argument of an exponential function needs to be unitless, meaning e to the something where that something has to not have units. Well, if time t is measured in seconds, then whatever is being multiplied by time t has to have units of per second in order for that exponential to be acting on a unitless function. So this would be negative 100 per second. And then we would have e to the minus 100 t prime evaluated at t and 0. What does that constant having a unit of per second do? Well, we have seconds multiplied by per seconds, meaning that now our voltage only has units of volts. So there's another reason why that particular coefficient had to have units of per seconds in order to make this math work out correctly. Okay. So doing some things here. Turn on calculator. There we go. So I have 8 divided by 0.2 times negative 100. That looks like negative 0.4. Now I'm going to do put my limits in here. So e to the negative 100t. What's e to the 0? Right? So this comes out to be 0.4 minus 0.4 e to the negative 100t volts. And converting it to millivolts, that 0.4 would look like 400. Any questions on problem 1 there? I know that you guys are probably thinking that I'm being overly meticulous with my units. I would vastly disagree. And as soon as you try these homework sets, I feel like you will too. Just as a heads up. Yep. All right, so let's look at problem 2. By the way, Hojun. That's correct. Actually, I probably didn't say memorize. I probably said learn, because there's a big difference between learning and memorizing them. And I highly encourage you to learn them. But yes, you will not be provided an equation sheet for exam 2. No, you will not. Yes. No, that was just for putting things into context. I will not expect you to know the permittivity of free space nor the permeability of free space, which I don't remember if I mentioned in the inductance video or not, but that is 1 over 4 pi times 10 to the negative 7 amps per second. No, Henry's per meter. Yeah. Must not have thought it was important at the time. And again, you won't need it for this class. Yes, ma'am. None. None. Yeah, we'll use that one a whole heck of a lot for exam 3. But for exam 1, or excuse me, for exam 2, I would expect the relationship, if I give you a mathematical function. So let's talk about something here. Okay. So this first problem is going to be very similar to what you might see on a test where I give you either a voltage waveform or a current waveform and expect you to calculate either voltage, current, power, or energy from that. For your exam, I would expect something that you could plug pretty much directly into your calculator to do the work with. So not anything as complicated as 5 + 3 cosine squared, blah, blah, blah. And by all means, look at the previous practice tests and make sure I'm not lying through my teeth here, but I don't remember ever giving anything wildly difficult like this one would be. Okay. The other type of problem that I like to ask for capacitors and inductors is a problem like this, where I give you a graph having either voltage or current, and I expect you to be able to calculate current, voltage, power, or energy from the parameters of this graph. So just as a heads up, exactly what I'm giving you guys on these ICAs are exactly what you should expect to see on your upcoming exam. And if you look at the exams, it should follow that through as well. Typically speaking, I give you one problem related to capacitors, the other problem related to inductors. One of them will be mathematical functions, the other will be a graph. One will involve integration, the other will involve differentiation. So that you have to know how to do all of it. Exactly right, which is arguably the hardest part. To some extent, yes. And if you look at your practice exams, you will see that there will be a problem in the capacitor and inductor section where I ask you to determine the energy stored in a DC circuit. So the energy stored in a DC circuit that contains both capacitors or both a capacitor and an inductor or something like that. And so the expectation there is that you can remember that the capacitor should look like open circuits, and you need to find the voltage drop across that open circuit in order to determine stored energy. And the inductor will look like a short circuit, and you need to find the current flowing through the short circuit in order to find the inductor stored energy. So I'll believe I answered that question. Okay. And again, all of that bears out based on what you should see on your practice exams. All right, so we have this graph related problem where we are told that the current flowing through a 5 microfarad capacitor is shown below if VC at t is equal to 0 is equal to 0 volts. And I ask you for the voltage drop at a particular time, the power absorbed at a particular time, and the energy stored at a particular time. Okay. So let's start with part A. We want the voltage drop and we're given the current. Okay. So much like in the previous problem, we know that the capacitor voltage as a function of time is 1 over C times the integral from T naught to T of IC of T prime dt prime plus VC at T naught. So for this particular problem, we are looking at T is equal to 5 milliseconds. So I'm going to put a dashed red line right here at T is equal to 5 milliseconds. We were also told VC at T is equal to 0. So the integral from 0 to T in this case would include all of this area. So how am I going to determine all of that area? Yep. So I personally would split this into 3 different areas. This area 1 is the area of a right triangle. 1/2 the base, which is 2 milliseconds, times the height, which is 15 milliamps. This area A2 is a rectangle, so it's just going to be the base. So 4 milliseconds minus 2 milliseconds looks like 2 milliseconds. The height is, once again, 15 milliamps. And then this guy A3 down here, the base is, it's a rectangle. The base is 5 milliseconds minus 4 milliseconds. So that's going to look like 1 millisecond. And the height is negative 5 milliamps. And then I add those 3 areas together. So 0.5 times 2 times 10 to the minus 3 over 15 times 10 to the minus 3 plus 2 times 10 to the minus 3 15 times 10 to the minus 3 plus 1 times 10 to the minus 3, negative 5 times 10 to the minus 3. Adding all of those things together, I get A total is 4 times 10 to the minus 5 amp seconds, which would be, actually, I'll leave it as amp seconds. Is that the correct answer? What did I forget? Times 1 over C. Very, very common mistake that I see students make is forgetting to multiply by a factor of 1 over C. So VC at 5 milliseconds is going to be A total divided by C, which would be 4 times 10 to the 5 amp per second, divided by 5 times 10 to the minus 6 amp seconds per volt. And these amp seconds cancel these amp seconds. We have 1 over volts, which is just volts. And I apologize. That should be a minus 5 there. So divide this answer by 5 times 10 to the minus 6. And I get 8 volts. So I'm going to leave parts B and C up to you guys, but let's talk our way through what would be going on there. All right. So for part B, you are asked to determine the power absorbed by the capacitor at that particular point in time. You already know what the current is because that's on the graph. So what would you need to do? Find the voltage at that particular point in time using the exact same process we just did. Multiply that value by 15 milliamps. There's your answer. For part number D, or excuse me, for part C, D wasn't even a number, my apologies. Determine the energy stored by the capacitor at T is equal to 1 millisecond. If we want the energy stored by a capacitor, what do we need? The voltage again. So we would find the voltage at T is equal to 1 millisecond, square that voltage, multiply it by 1/2 C, and there's our answer. So this one is just literally beating you over the head, trying to make sure you know how to find the voltage if you were given a current waveform. For a graph problem like this, so on the exam, you should expect something of this level of difficulty where you can find the area by just adding triangles and rectangles. So I would argue that it's probably not worth the time to get a mathematical expression. All right, let's look at problem 3, okay? So this is capacitor combination, okay? For the capacitive network below, determine the equivalent capacitance seen between the terminals with the switch opened or with the switch closed. So I'll work one of these with you guys. Do you want switch open or switch closed? Closed, okay. So closing the switch, let's identify our terminals, or excuse me, identify our nodes. So that's going to be 1. With our switch closed, this is 1. Then we have this guy. Now we have this guy, and now I'll label things. So let's call the red node A, the blue node, dark blue node B, the green node C, the pink node D, and the light blue node E. So if I'm finding the equivalent capacitance seen between terminals A and B, I'm going to treat this exactly like a resistor problem. I put A and B on opposite sides of the page, and now I'm going to play connect the dots. So there are multiple different routes that I can take. So let's start with what's probably the easiest one, which would be around the outside loop, right? So going from A to D to E to B. So let's put D here, E here. From A to D is 11 microfarads. From D to E is 5 microfarads. From E to B is 18 microfarads. And we have our outside loop taken care of. All right. The other path that we could take would be to go from A to C to B. So I'm going to put C here in the center. I can go from A to C in two different ways. I can go through the 4 microfarad or the 18 microfarad. And to go from C to B, I have two different routes, the 15 or the 25. All right, so what's 4 microfarads in parallel with 18 microfarads look like? 22, yeah. So when capacitors are in parallel, you just add the values together. So 4 in parallel with 18 is going to look like 22. 15 in parallel with 25 is going to look like 40. $22 in series with 40 is going to be 22 times 40 over 62, right? $14.194 and some change. I'm just going to store that in my calculator as X. For that topmost path, that's going to look like 1 over 11 plus 1 over 5 plus 1 over 18. Take the reciprocal of that whole thing. 990 over 343 microfarads. Now I'm going to have x times y over x plus y. No, that's wrong. Just add them together. My bad. X plus y. 17.0798 or 17.080 microfarads.